So you probably know that Pages has a cluster of projects grouped around the idea of warm worlds, with the idea that if we look at worlds in the past that were warmer than today, we can learn something about the future that we're coming to, which is, we're pretty sure, going to be warmer. It seems to me that I'm kind of representing all of those groups, although some of them probably wouldn't recognize me as a representative. So I'm going to say something about that in general, and then move on to talk about the interglacials in particular, and especially based on work done in the past interglacials working group, PIGS, and the Quaternary interglacials working group, QUIGS. I think we're moving through the alphabet slowly. And my feeling is that these plenary talks, they're meant to be a little bit educational. Although we all work on paleoclimate, there are many people here who I've never met before who work on completely different topics. And so I apologize to the maybe 10% of the audience who are very familiar with interglacials, that it will be old hat to you, but for the other 90%, maybe it won't. So when we're using warm worlds of the future to inform us, or warm worlds of the past to inform us, I think you have to think that there's a balance between two things which unfortunately are in opposition. One of them is the amplitude of the warmth and how much the past feature is like what we're expecting in the future. In other words, we're looking for a big signal like we're expecting by 2100. But set against that is the quality and quantity of the data that's actually available. So there are various warm or high CO2 periods we might hope to use, and I've listed them there. I don't necessarily need to spell them out, but in case you don't know, they go right back to the early Eocene, which isn't really Page's territory, but nonetheless it's a warm world that people use. I think firstly you have to assess how these different periods fit in to what we're expecting in the future. So on this plot, you can see I've plotted on the CO2 concentration expected under the IPCC representative concentration pathway 2.6. So that's the one where we make heroic efforts to stop emissions, the one that we've already failed to meet. And RCP 8.5, which is the one where we do nothing. So you see you get to either just over 400 or about 900 parts per million by 2100. So you can already see why we have a problem with using the past as an analog. Probably the only time I'll use that word. Because certainly nothing in the Quaternary comes anywhere close to 400 parts per million CO2. The mid-Pliocene is just about there, but you have to go back to the early Eocene to reach the RCP 8.5 concentrations. And similarly, if you look at global mean temperature with all its huge uncertainties as you go back in time, if you want to go to the RCP 8.5 world, you've certainly got to go to the mid-Pliocene and heading back a little further than that. So that's just a context as to which periods we can look at where you have a big signal to look at. But then the countering problem is whether we have evidence about that big signal. So we know everything about the future. That's the first thing to say, because our models tell us everything. They tell us global fields of everything seasonally, everywhere. And we know a lot about the last 30 years thanks to satellites. But as you go back in time, the nature of the evidence gets more and more diffuse. So over 150 years, we feel confident about making a global mean temperature, but we don't feel too confident about some other things, and we don't have data from some places. You go back 50,000 years, we at least feel we know what time period we're at because we have radiocarbon age control, and we can line up data from, say, Greenland and Antarctica, as I've done there. You go back 800,000 years, it becomes much harder to even line your records up and say, what happened in Central Asia at the time when this happened in Antarctica. But at least we know what the forcings were because we've got that from ice cores. Now, normally as an ice core person, I would stop at this point because there's nothing interesting before this. But that was done specially for the Pliocene people. So, but, okay, then you go back a bit further, and at least over the last 60 million years, we've still got marine sediments, so we know a little bit more. We have a chance of getting sea surface temperatures, of getting at least a proxy we kind of believe for acidity of the ocean and therefore CO2. I've marked on our time periods there, so there's I don't think this reaches, does it? Ooh, yeah, you can just see it. The early Eocene, the Paleocene, Eocene thermal maximum, and the mid-Pliocene, sorry. And then finally, before that, we know almost nothing, so I'm not going to talk about that. So we have this balance of finding periods with a global change comparable to that we expect by 2100, but that means we have to go into time periods where it's really challenging to know anything. It's really challenging to put things on the same timescale. For instance, to be sure whether this record's from one part of an orbital cycle and this record's from a different part of an orbital cycle, and yet I'm putting them together. That doesn't mean it's not worth doing. It is, and you should go to the Pliocene session tomorrow afternoon. Not all of you, otherwise it gets uncomfortable in that room. It's important and it's worth doing because those are periods where there's such a big climate change that you've got a chance of critically evaluating the really large concepts like climate sensitivity and does polar amplification occur and how's the land-sea contrast looking. The more recent periods, we clearly don't have the kind of changes we're expecting by 2100. We've got regional climate changes, but not the same level of global changes. But interglacials in particular, which is what I'm now going to focus on, they have their own value for warm world studies, and I'm going to use as my example the one that is most close to my interests, which is the polar impacts. And again, there's a session, or there are several sessions you should go to. There's a pre and post MPT session on Saturday morning and interglacial session today. But I'm also just going to discuss interglacials in their own right, not in the context of warm worlds. So okay, that was the introduction. That was hopefully enough that everyone who's coming this morning is now sitting down, and now I can get on with the real talk. So, interglacials. We've seen this plot a few times, if you've been in any sessions at all. So this is the Lisiecki-Ramo benthic isotope stack. We know it represents some kind of combination of ice volume and deep water temperature. So what you see is the interglacials are the bit sticking out at the top, because I've turned the axis upside down. So these are the interglacials. And they're the warmest periods we can look at where we've got, well, okay, at least for the last 800,000 years, they're the warmest periods where we've got a lot of data on both the climate forcing and the response, so that makes them really good. Before that, the climate forcing data is a little bit more diffuse, although the ice core community does hope to take you back that far, eventually, but probably not by the next Pages meeting, so don't hold your breath yet. So it gives us lots of examples of a period that's as warm as today, at least. But of course, the reason for the warmth is not carbon dioxide, and it's unlikely to be global. I'll come back to that. So we just have to be aware of that when we're looking at the things that we see in past interglacials. And of course, particularly we're interested in as well in the transitions into interglacials. I'm going to talk about that a bit, that's why I've mentioned it. So here's what I'm going to talk about. I'm going to talk particularly about how warm, how intense different interglacials were. And again, I have to apologize because some of you will have seen that part before, but many people won't. And then I'm going to focus in eventually on one particular example, which is about the last interglacial and sea level. A lot of what I'll be saying in the beginning of the talk comes from a review paper of the Pages Pigs Working Group, and I can refer you to that if you've got a spare few hours. Okay, so the first thing to say is what is an interglacial? And actually it turned out in the Pigs and Quigs review group that question, which may seem rather stupid because we'd already formed a working group, that question led to some interesting insights, I would say. So we ended up defining interglacials based on a kind of sea level definition, but actually, to be honest, our sea level records are not sufficiently consistent between themselves to use just that. So we extended it by using LRO4 criteria for what made interglacial. And I'm not going to go into that because although we found it endlessly fascinating, I've realized in successive talks that other people don't. So all I'm going to say is that we ended up saying there are 11 interglacials in the last 800,000 years, which is perhaps rather more than you think, because we ended up saying that 7E is a separate interglacial from 7A to C, and 15A is a separate one from 15E. And you have to do that, because if you don't do that, you'll end up saying that all of this is one interglacial. It has some interesting consequences, because if you do that, you immediately stop thinking that interglacials are spaced by 100,000 years. And although they kind of are, it's helpful not to think of it that way. Okay, so there are all these interglacials, but they're all very different. So these are just two examples. Some of them are very long, some of them are very short, some of them are strong, some of them are weak. So the first question we asked was, which are the really strong ones, the ones that we might be most interested in, especially when we're thinking about future warmth? And this arose partly from the ice core community, so it's partly my fault, I suppose, because we put forward this idea that after the mid-Bruners, which is there, the interglacials were stronger, and before it they were weaker, and that there might be something we really needed to understand there. And that's kind of evident in these ice core records. That's methane, CO2, and deuterium, so the temperature proxy. But is it true elsewhere? Okay, so what we did, I'm going to show you, there's coming up in the next slide a very complicated table, and I need to walk you through it so it's not so scary. So what we did was to take the maximum value in each interglacial for a particular parameter, in this case the LRO4 oxygen isotope, so it's the minimum value because minimum means strongest. And we looked at all the interglacials, whoops, we did, 1, 5e, and so on to 19. And we said which is the strongest, and the strongest one is coded in red, and which is the weakest, and the weakest one is coded in blue. Right. So then we looked at all the sites where we thought we had long, continuous, well-resolved records. Well-resolved means 3,000 years, something like that. Right, here's the scary table. So now, bearing in mind what I said before, what we've got here, we've still got the interglacials running along the top, and down the side we've got, these are all SST, sea surface temperatures, except for the bottom one, which is Antarctic temperature. And they run from high latitude in the north to high latitude in the south in order. If you're really interested, that's the ocean basin. And all you're supposed to get from this is that where you see a column with a lot of red, that was globally somehow a rather strong interglacial. Doesn't mean it was warm at the same moment in the interglacial, it just means at some point in the interglacial it was warm. And where you get a lot of blue, it means it was a weak interglacial. So the first thing to say is that our thought that the interglacials after here were stronger is kind of generally true. There's more red on the left of the diagram and more blue on the right, but it's not a rule. There are definitely ones over here which would perfectly happily sit over here, and there are ones over here which would be reasonably happy sitting over there. So there isn't some kind of really secular change at 450,000 years. There's just a tendency to stronger interglacials. You also see that stage 5 is very red, stage 11 is pretty red, stage 9 is kind of red, and stage 13 is blue. So I'm going to summarize that in text next. Okay, we'll jump over that. No, I'm not. I'm going to also look at some other things. So we've also got on here things like CO2, and we've got some terrestrial records here. They're a bit more mixed. So you remember 5e was very red, but in the terrestrial records, 5e's not always red. It's not red in Lake Baikal and Lake Elgigitgin. Stage 11 is. Stage 13 even is strangely red in some records in Asia, even though it's very weak in the sea surface temperatures. So just bear that in mind in what I say in the next slides. So in general, what we learned is that MIS 5e and 11c are generally warm at global scale. That's to say there is warmth at some point in each of those that stands out compared to other interglacials. Stage 9 is also rather interesting because it is very warm in some records, but it's warm for a very short period. It's very sharp. And I think some of us have the feeling that stage 9 might actually have been a rather exceptional interglacial, but in most records we just don't have the resolution to see that. And I'm not sure whether we can get to that, but it's a challenge to people out there to get more well-resolved data for stage 9. It might turn out to be very interesting. Okay, I've only talked about the last 800,000 years, but there is this question, should we be looking in the context of warm periods at some of the earlier interglacials? Are there ones that are more extreme than stage 5e and 11? I should say the only reason why, just so you're not confused, the only reason I've made it red over here is because I've actually smoothed Lisiecki and Ramo on the left because it's at a different resolution. When you just download the data, it's at a different resolution to the bit on the right. So in order to make a fair comparison, I've resampled it so that it's all at the same resolution. So that's just to tell you that I've played with it a little. So I think we all have a feeling that there's a warming here. So you might expect very warm interglacials over here. But actually, when you look at it and draw a line on at the stage 5e level, there isn't actually anything in Lisiecki and Ramo that's stronger. Whatever that means, this combination of two things, there's nothing in the whole record that's stronger than stage 5e. Stage 31 I've marked, which is very famous because it's got the strongest northern hemisphere insulation forcing, because it's got a strong combination, very strong precession and strong obliquity. But it's still not stronger than stage 5e or 11 in Lisiecki and Ramo. And if you look at a global SST synthesis, oh yes, that's just to warn you, I've tried to make time run in one particular direction, which I know, whichever direction it's running in, to defend someone in the room. In this one, time's running in the opposite direction to everything else in the talk, so just be aware of that. So this is a sea surface temperature synthesis. It probably has some problems with it, with the way that it's been done, but nonetheless it's there and it's worth looking at. And again, you see this warming as you go back to the early ones. But actually, you probably can't see from there, but if you don't get distracted by the blue line, which of course gets fatter as you go back in time because we have less data, that's the uncertainty. If you just concentrate on the black underlying line, there still isn't anything stronger than stage 5e in that plot. 5e is still the highest point on the black line. So I'd say these early interglacials, they're very interesting for all kinds of reasons, but as far as warm worlds is concerned, if we're just interested in looking at something warmer than today, 5e and 11 are more obvious targets just because of the amount of data we've got. We may see some data tomorrow in the session which makes me change that view because we're going to have some very nice new data sets, but at the moment I would concentrate on 5e and 11. I just wanted to add this because I think we rarely think about this. I hear people searching for a really warm interglacial, a globally warm interglacial, and I think we should just step back and think about the physics for a minute. We shouldn't really be surprised that we can't find a hot interglacial, because we are stuck with the physics of energy balance of the planet. And if you want to warm the whole world by 2 degrees, you've somehow got to play with something else in this equation. And if we're not going to play with the emissivity, or at least not with the emissivity we're playing with, if we're going to say CO2 wasn't higher than today, which we think is probably true going back over this 2 million years, more or less, then you're going to have to do something fairly extreme to the albedo to get a world that warm. And of course you can do it. It is possible. You could have cloud feedbacks, you can have ice feedbacks that do that. But I don't think you should expect to find very warm interglacials back there in the absence of a change in CO2. Okay, I'll very quickly talk just about a couple of other things, features of interglacials that aren't really particularly about warm worlds, but just because they're important aspects of interglacials. And we shouldn't ignore this idea that there's something strange about marine isotope stage 1, the Holocene, because CO2 increases. And Bill Radiman, in a collection of papers, has suggested that that's anthropogenic and that it stopped us going into an ice age, which is a very compelling idea for the press. It's a very interesting idea. Some of us aren't totally convinced by it. And all I wanted to do in this talk was just to say that his argument is that in most interglacials, CO2 decreases. And he's right, in many interglacials, CO2 decreases. And in stage 19, which we think is the closest orbital analog to our present one, it decreases. So you could see the trend in stage 1 as being odd. Stage 5e, it's kind of flat, but there are also ones that do what happens in stage 1. There are at least 2 interglacials where CO2 increases once you start to get into the interglacial. And if Bill was here in the room, I don't think he is, if he was here in the room, then he would say, but that's because they're orbitally different from stage 1. And he's right, they are orbitally different from stage 1, but I have yet to see a convincing argument for why orbital characteristics should directly control CO2. So I think I only wanted to introduce this to say, in case people think this is now a settled idea, because I think Bill's written so many papers about this that there's this feeling that somehow this is now the truth, but it's still a very open question as to whether stage 1 CO2 trends are natural or anthropogenic. And I think we can argue it either way based on analogues, and we need to sort it out through physical modeling, not through just staring at these records. I want to say something about terminations, which are interglacial onsets. They're not, okay, you can think of them as glacial terminations. I like to think of them as interglacial starts. So that's where they are. What is a termination? So you can kind of see on here. So firstly, everything changes in a termination. Benthic isotopes change, CO2 changes, methane changes, so that implies that the wetlands are changing. Temperature in Antarctica changes, temperature everywhere changes. Over a period of about between 5,000 and 10,000 years. The change isn't simultaneous or of a similar rate in different components. Some things jump, some things go very slowly. Not fast in comparison to the length of a glacial cycle, but slowly compared to a rapid jump. I'm going to jump over some of the ideas on this slide and just talk briefly about the fact that, which is one of the things that I think has become very apparent over the last few years since the last Pages meeting probably, that the onset of interglacials seems to always include the fingerprint of a bipolar seesaw, millennial scale change of the kind you see in a Danskar-Oeschger event. You can see it on here that you see that it's stage 5e. You see that Antarctica, because this is Antarctic temperature on the right, Antarctic temperature slowly ramps up and CO2 does the same thing. Whereas methane, representing something kind of northern hemisphere, at least it's very closely related to northern hemisphere records, methane waits, it does slowly ramp up, but then it waits and then it suddenly jumps up afterwards. And it does the same in each termination. Stage 1 is actually annoyingly complicated, and it's probably confused us over the years because it's got this complication that it does it twice, having the Alarid Bulling and the Younger Dryas in the middle of it. But there's always this fingerprint of a bipolar seesaw in the terminations, and I think a good question, which I think many of us think is now answered, is that essential to the termination? And I think the answer is probably yes. And is it inevitable? I think the answer is also yes. And the reason it's inevitable is because you get a lot of meltwater at a termination, so you're bound to get bipolar seesaw activity. And the reason it's essential is because this is actually the way you start the termination. So I think when you're thinking about the timing of interglacial onsets, and I'm not going to go into this in detail, you need to think of it in a hierarchy of timescales. In general terms, a termination occurs in the classic Milankovitch idea of when the Northern Hemisphere summer insolation is rising, which is how you melt an ice sheet. But it doesn't happen in every precessional cycle, and that's what makes it so difficult to understand exactly how Milankovitch cycles work, and why when we lecture our students, we tell them it works, and then they come up to us and say, but this record doesn't look anything like Milankovitch forcing. What are you talking about? So knowing which precessional cycles is determined by a combination of the insolation, which involves obliquity as well, and the size of the ice sheet, which is somehow history. And I refer you to Chronis Sidakis' talk tomorrow to hear at least a description of how that works. So that's telling you which precessional cycles, but then there's also the question of precisely how is it phased compared to that Northern Hemisphere insolation, and that seems to depend on this millennial scale bipolar seesaw activity, which will determine when you see it at a particular place in the world. So you might see it earlier in Antarctica and a bit later in methane, for example. So my final topic, that was a little disconnected from the warm worlds bit. As my final topic, I want to talk about stage 5e and 11. And particularly, it'll mainly be 5e actually, but I'll come back to 11 at the end. And one characteristic that I think is really important is that we know from the people doing work on corals in particular, that both of these were times when sea level was higher than today, and it's quoted as 6 to 9 meters for 5e and 6 to 13 meters for stage 11. And that's a lot of sea level. We think, even if it's going to take thousands of years, we think that that's something that people probably should know about. So let's talk about the last interglacial, stage 5e. There's the timing, there's all the different names you might use for it. Well, not all of them, there are some others. So the question, I have used the word analog again, I'm sorry, I'd forgotten. Is it an analog for the next century? So the answer is yes and no. It's yes because it's warmer than present, and particularly in the polar regions. And no because the causes of warmth were different, which means that the distribution of warmth throughout all these things, seasons, latitudes, and ocean depth, is very different from what we're expecting in the future. So you certainly can't say that stage 5e is like the future, and saying what happened to sea level when it was 1 degree warmer than present is kind of irrelevant. What you want to know is what happened to sea level when the polar regions had a particular temperature. There is a sea surface temperature synthesis which tells you that it was warmer than today, and I think we saw that when we did our work as well. But let's concentrate on the polar regions for now. So at the top you've got in red, you've got Antarctic deuterium, so that's Antarctic temperature, and the blue line is the warmest period of the Holocene. So you can see that it was substantially warmer in Antarctica during the last interglacial. We estimate 3 to 6 degrees. At the bottom is the NEAM reconstruction from Greenland ice cores of temperature, which is a little more complicated because it involves reconstructing some ice that had been deformed. But nonetheless, I think that's probably a reasonable reconstruction of temperature in Greenland, which also was warmer than the present, or warmer than any time in the Holocene by several degrees, as you can see. So how do those number of degrees stack up against what we're expecting in the future? So this is a plot like those ones early in the talk. You can see that the last interglacial warmth in Greenland over here and in Antarctica over here is really very comparable with what we'd expect under RCP 8.5 by 2100. So it's something that if we don't do anything about CO2, that's what's going to happen to the polar regions. And unless CO2 is actively removed from the atmosphere, models suggest that it will take a very long time for temperatures to return to normal. So even if we stop emitting in 2100, it's going to stay that number of degrees warmer in the polar regions, more or less for several hundred years to several thousand years. So in that sense, stage 5e is an analog for a world that we could be in 2100 if we do nothing about reducing CO2 emissions, and if we then, for the next few hundred years, do nothing about removing from the CO2 from the atmosphere. And sea level, as I said, was 6 to 9 meters off. It was about 6 to 9 meters higher. This is from Andrea Dutton's paper. It's actually a slightly strange plot in that it's studies through time. So it says what sea level estimates were through time and how they've converged on this 6 to 9 meters number. 6 to 9 meters, you can get about 1 meter out of mountain glaciers and ocean thermal expansion. So we need to explain 5 to 8 meters based on the Antarctic and Greenland ice sheets. And a similar plot at the bottom here, people believe that from Greenland you can probably only get maybe at a maximum about 3.5 meters of sea level equivalent. But estimates are converging on around 2 meters. That's because you're constrained by the fact that we found interglacial ice in most of the Greenland ice cores that have been drilled so far. And you also know roughly what the height of the ice sheet was at some of those sites. And that constrains what the models can allow you to have from Greenland. So that implies there must have been a major reduction in the Antarctic ice sheet. And it could be from East Antarctica, it could be from West. De Conto and Pollard recently suggested that this is what the West Antarctic ice sheet would have looked like in the last interglacial. And you can see it looks very different from today. So I think we as a community have what I call a last interglacial problem. The best evidence is for a sea level rise of 6 to 9 meters, which at the lower end requires a significant loss of both Greenland and West Antarctica, and at the upper end definitely requires some of East Antarctica too. So the implication is that a warming like the one we're expecting both in the Arctic and the Antarctic, I've concentrated on the Arctic here, sustained, is enough to cause a major loss of the Antarctic ice sheet, which, as I've said, given polar amplification and given the longevity of warming if we don't remove the carbon, is well within what we could be committed to by the end of the century. And so we should be shouting about this. We should be saying this isn't just models. Actually, the data shows that under the conditions we're going to be in, sea level was 6 to 9 meters higher. But we can't shout about it because we can't put our hand on our heart and say we know where the ice came from. And I feel quite passionate about this, as you maybe can tell. I feel we should, as a community, be able to tell people whether the West Antarctic ice sheet partly disappeared in the last interglacial. We should be able to give really good confirming evidence, and that's what I'm going to be working on mainly in the next 5 years myself. But it's a challenge to anyone else out there. If you can do it, then we can really shout about this message that sea level and warming is a problem, that we can actually show evidence that it happened in the past. We could also look at stage 11. It's a little bit harder because we don't have a Greenland ice core to know what the climate was there, and we've got less chance of diagnosing what happened to the West Antarctic ice sheet as well. The sea level seems to have been higher in stage 11 than in stage 5, although it's very uncertain. And there is data showing that South Greenland at least was lost. So it could be, in my mind, that you can explain the difference between stage 11 and stage 5 just by saying that more of Greenland disappeared. So I don't think it's actually a different problem. So I think if we can understand the stage 5 problem, we've probably understood the stage 11 problem too. So just in summary, we do have something to say as a paleo community about what could happen in the future, and we should make sure that we do work to concentrate on that. There's a fascinating zoo of interglacials to study. However, no interglacial mimics the expected future change, but that doesn't mean they don't have characteristics we can use to explore the responses to warmth. And I've concentrated on the polar regions and sea level, but you could look at temperature gradients and talk about atmospheric circulation, for example. You could look at characteristics where the interglacials might have different hydrological characteristics to the present, which in some regions will be like what we're expecting, and look at the ecological responses to that in those regions. Stage 5e and 11 seem the most promising for doing this, and the sea level in stage 5e in particular is not at all reassuring about our future, but I think we urgently need to be able to explain which ice sheet, or whether it was both of them, was affected and why, because either our models are way too sensitive, or the current ice sheet models are way too sensitive, or there's some problem with the sea level records, or we're just not seeing something that's such a gross feature that we really ought to easily be able to find it. And with that, I'll stop. Thank you.